Previously, we talked about an example to determine the slenderness of a column. The calculations process involved calculating the slenderness ratio on the basis of the effective length and the radius of gyrations. The calculated slenderness ratio is later checked with the slenderness limit in order to determine whether the column is short and slender. The calculated result shows that it is a short column. The equations to determine the slenderness limit in the example we use this. In fact, there are three equations to determine the slenderness limit, subjected to various conditions. We mentioned briefly how these equations are selected, but it is not justified when we use these equations in the example. In these videos, we're going to talk more about the selections of the equations, demonstrating the circumstances when these equations are adopted. The selections of the right equations is very important because this shall ultimately govern the slenderness limit. If you observe the equations, these equations going to give you the largest slenderness limit, whereas these equations will give you the smallest slenderness limit. Since the parameters governing the slenderness limit are the same, the main difference it will be the constants as a result of the computations of these ABC constants. Now, if you see the examples that we did previously, the slenderness ratio calculated are here. If we use these equations, the slenderness limit is relatively large and it ends up to be a short column. But if we use these equations, the slenderness limit will reduce significantly. For the same set of slenderness ratio, it might end up to be a slender column. This establishes the importance of selecting the right equations as the slenderness limit. You might misjudge the type of the column if you use the equation wrongly. Now, coming back to the questions, in our previous videos, we simply assume that these equations is being adopted without much further explanations. You might be asking whether the selections of these equations is correct or not. If you have been asking about this, good for you. That means you are thinking and seeking for answers. In order to determine the equations to be used, we will need to look back into the design assumptions, particularly the loading conditions of the column. Before we reach to the conclusion, let us first establish the basic principles. The three equations here are derived from the set of equations here. Theoretically, you're going to compute every single one of them in order to get the exact value of the slenderness limit. However, due to the complexity of the calculations, we tend to simplify the calculation process on basis of a series of assumptions. These assumptions may not be accurate, but it is good enough to cover the critical state under different conditions. That means, as long as we can accurately identify the type of conditions, the equation shall be safe to be used. It might not be accurate, but it is safe. If you want it to be extremely accurate, you should look into every single symbols here and substitute with the correct value. That means by using these equations, it is already simplified process, catering for different conditions. Now, the conditions shall be based on the response of the column as well as the moment acting onto the column. This response of the column shall govern the ratio between M02 and M01. What are the M02 and M01? They are referring to the moment calculated from the analysis of the column. You see, a typical column has two ends. Each end meets to a joint. When the joint is subjected to the moment, due to the stiffness of the column itself, the column shall share part of the moment acting on the joint. Depending on the relative stiffness over the total stiffness of the connection, you will be able to get the moment taken by the column. Both ends might have different setup of the connections. Taking this as an example, you have moment in the major axis, and you have only one main beam from one side of the column. That leads to you the connections constitute of 1 and 2 members. Plus the upper column, you have only 3 members in the joint. When there are less members involved, the stiffness relative to the total stiffness of all the members joining together, it will be relatively high as compared to this end. Ultimately, it may lead to a situations, different moments taken by the column at different ends. That leads to you M02 and M01. N02, it will be the larger moment, whereas the N01, it will be the smaller moment. Now this Rm, look into the ratio between the smaller moment against the larger moment. When the Rm here varies, this shall influence the C and subsequently influence the slenderness limits. Now, having this understood, let us look into the classifications of the conditions of the column. There is one common misconception. Most students assume that this equations is applicable to only the unbraced member. In fact, this equations is also applicable to the braced member. In another word, for a braced member, all these 3 equations can be used. This equations is more critical than this, and this equations, it will be the most critical for the braced member. Having this misconception clear out, now we're going to look into this example. The question states here it is a braced structure. For you to determine the slenderness limit, you're going to use any of these 3. Now coming back to this question, which equation shall be used? Why do we use this instead of using these 2? To answer this, let us first look at different load arrangement. The loading arrangement shall govern the moment acting onto the column, which subsequently will govern the response of the column. Let's say now we are dealing with this column. We are designing the column on basis of the critical load arrangement. That means the priority, it will be to generate largest moment acting onto the member as possible. For the upper end, the largest moments acting onto the column end here, it will be having this to be the maximum, since you don't have any beams here. As for the lower end, you can have either maximum here and minimum here, or minimum here and maximum here. Now if you refer to the key plane, both lengths are the same. That means the locations of the maximum and the minimum are not fixed. It can be in this manner, and it can also be in this manner. In the case that the span here are different, when this span is longer than this span, you will put the maximum here, where else the other side will be the minimum. In the case that this span is longer than this span, you will arrange the otherwise. Now the maximum shall be here and the minimum shall be here. So in this case, both cases are valid. Both can happen in this structure. We have another possible setup just for the sake of demonstrations. Let's say now both sides are of maximum load, and when the span here and here are the same, the fixed end moment generated by both beams shall cancel out each other, ultimately leading to zero moment here. I guess by now you should be able to determine which equations to be used in accordance to the load setup. Let us first start with this setup. Maximum load here will lead to rotations of the joint here. Imagine due to the moment, the horizontal axis of the joint now has been rotated, giving you a slightly inclined joint here. Remember that concrete structures are monolithic at the joint. The meaning of monolithic is that we assume all the members are perpendicular to the joint. That means 90 degrees to the axis of the joint. Because of the rotating moment here, the joint goes inclined, and the column will have to be 90 degrees to the inclined axis of the joint. This leaving you the column should go in these directions. And then let us look at the joint here. Maximum load here, minimum load, giving you a resultant moment, causing an incline of the joint axis, and then the column is 90 degrees to the joint. That means this end shall go here. Having both end directions decided, now you will need to join the columns. This is when you predict the response of the joint due to this load arrangement. Most likely your columns will end up something like this. Knowing the deformations of the column, these deformations it will be same as in this one, which give you the equations of the slenderness limit of this. And this is applicable to the brace member as well. Now you know that this setup shall have the slenderness limit of this equation. Let us look into the second load setup. Again, maximum load here. Both sides maximum. When the spans are the same, and when the loadings are the same, there should be no resultant moment. Without resultant moment, the axis of the joint does not rotate. Your column will still remain 90 degrees to the axis. As for the top end of the column, because of the resultant moment here, the joint axis rotated 90 degrees to the joint. You will expect the column deform in this shape. 90 degree here and 90 degree here. This gives you some moment here and 0 moment here. If you refer to the table here, you have one side with moment and another side without moment. That means you should use this as the slenderness limit. This equation is also applicable if you have the top moment 0 and bottom with moment. That means it is also applicable when the moment diagram is inverted. The main thing here it would be one ends with moment, another end with 0 moment. Now coming to the third look case. Same thing. Resultant moment here causing you the joints to be rotated 90 degree to the joint connections from the column. You know that the column should orientate in this direction. Now when this side is maximum and this side is minimum, the resultant rotation shall be in these directions. That gives you the changes in terms of the connections axis. 90 degree to the joint, you will expect the column in this curve. Referring to the table here, in this response of the column, you will use this equation. Now having this understood, we go back to the questions that we have posted in the early of the videos. Shall we use these equations for this example? The answer lies into the design arrangement of the loop, as well as the strategies that you use to design the column. Especially for this case, when both spans are the same, that means this can happen and this can happen in the extreme case. And you know that these equations, it will be the most critical. If you use these equations, this column might end up to be slender column. Of course, you can go for this as the slenderness limit, which may result in highly conservative design solutions. Now it goes back to your design strategies and your assumption. You may also consider from another aspects in terms of the moments acting onto the member, whether this moment is relatively large or small as compared to the sectional properties of the column. When the moment is relatively small to the capacity of the column, or more specifically to the capacity of the connections, you will expect little deformations of the connections, which the deformations of the columns may not be as critical as this. Now if you are unsure, you know that this load arrangement is going to give you the most critical slenderness limit. Probably you will use this as the slenderness limit for the questions of the brace structure, and as a result, the columns shall eventually become the slender column. And what would be the implications when a column changes from the short columns to the slender column? The implications, it will be the calculations of the MED. The MED for the slender column would be affected by the second order moment, which may end up to be slightly larger than the short column. And as a result, while computing the required reinforcement bar based on the design chart of the column, larger reinforcement bar area may be required. This will end up to be a more conservative design. Now in the case that when this span and this span are of different length, the maximum load shall go with the longer span. If this span is longer, this side shall be the maximum load. Then without doubt, you're going to use this equation. In the case that this length is longer than this one, that means maximum load should go this side. Therefore, you should use these equations.